There we go, starting the recording. Officially a few minutes late, but who cares? Welcome back. Happy Thursday. Thanks for being flexible with me for teaching from home. My son is homesick from school. He's not too bad, but he's one of those kids that doesn't ever lie to try to get out of school. He just whines a lot. So, like, I'm inclined to believe him when he actually tells me that his head hurts and he feels like throwing up and his nose is stuffy and all the things. So, like, yeah, that's no fun to be sitting in school like that. So he gets to have an extra home day. Fortunately, I'm not sick yet. That's the good news. Normally, if this were to happen, then I would have my husband take over, but he is out of town. He's the outest out of town I think you can be. He's in South Korea this week for a conference. So we joke that he calls us from the future, like at breakfast. He tells us how Thursday is going to be, that kind of thing. So hopefully he is asleep right now. And here we go. Zoomers are still coming in, so I'll be manning the doorbell. I am going to turn things over to the TAs who are going to be talking about the formative assessment questions. So Ten is going to do the first two over compound symmetry and unstructured. Bladimir is going to do the last two about RNG and ACS models. And given that you all can have the questions in front of you, I don't think we need to have the screen share on, so I'll turn it off for you. The YouTube video will have this screen on for like a half hour, but that's too bad. So, all right, let's see. 10, go for it if you want to take over here. And let me know when you want
Great.
the slides up.
Yes, I think we'll keep them down for now.
Okay.
Um, so, as is usual with the formative assessments, the TAs and Lisa, we've all kind of reviewed them and whatnot. I'm in charge of the first two, and you all did fairly well on them. So I'm excited to review these two questions with you. So the first question is, what pattern of variance and covariance over time would a compound symmetry model predict? I'm gonna hold off on the second part of the question.
Both the variance and the covariance are held constant across time.
Yes, excellent. So we're seeing that also in the chat from folks. So there's one variance predicted at each of the occasions, and then there's one covariance for each of the combinations of all of the different um, cross. What's the word that I'm looking for, Lisa?
Pairwise occasion?
Thank you. The pairwise occasions. So what does that mean if we had 4 occasions? How many parameters do we have? This could be a finger question. Yeah, I'm seeing lots of 2s. Excellent. Yes. So a bonus question, what would happen if we had 5 occasions? How many would it be? 2. Yep. What about 100 occasions? 2. Yes, excellently. Lisa, do you mind pulling up the slide so that we can talk about this? Great job, everybody. So we did have some questions about matrices and different things like that. So I do think it's helpful to just kind of talk through this slide. For the YouTube recording, it's lecture 4, slide 11. And what we can see, it's so funny because Lisa, you are driving, not me. So I just started hovering over things. So
Good
along
luck
the
with that.
diagonal, that's essentially representing each variance. So in the top left corner, we've got occasion 1. That's the variance there for occasion 1. And then we move down to occasion 2, occasion 3, and occasion 4. And then you can see the CS's in the off diagonal. That's what it means when you're moving away from the diagonal. That's all one covariance that's essentially being held constant. And one thing that's a property of matrices, well, at least in this case, I guess yes, in this case, is that they're actually mirror images of each other, which is hard to tell in this one. So stay tuned for question number 2. Any questions about compound symmetry? Great. I think we can move on to the next one then. Lisa, you can stop sharing if you want. So then the next question is, what pattern of variance and covariance over time would an unstructured model predict? I know folks did really well with these ones.
So this one, it's for unstructured, it's not like a model, right? It's just data, so it doesn't predict anything.
Yeah, it's just representing what's happening in the data. Absolutely. So I'm seeing some things in the chat. All variance and covariance are estimated separately and will be different every time. Yep, unique variance and covariance estimated over time. Yeah, absolutely. And so if we have 4 occasions, how many parameters is that we would estimate? Yeah, this is actually a finger question, and I wonder if Lisa did it on purpose. 10, absolutely. So folks talked about having 4 separate variances. Again, that's on that diagonal for the matrix. Lisa, you can go ahead and pull it up. And then you're going to have 6 covariances. And so if we look at the matrix here, again, across the diagonal, we're seeing all those variances, but now we're seeing a 1, 1, 2, 2, 3, 3, 4, 4. And so each of those are allowed to be different. And then if we look essentially at the bottom, if we look at the bottom, Ahmed, I'll get back to your question in a second. So then if we look at the bottom of our matrix, those describe our covariances. And the way it works, if we look at cell 2, 1 and 1, 2, so it's like sigma 2, 1 and sigma 1, 2, that's essentially the covariance for 1 and 2, or the covariance for 2 and 1. And so you can kind of think about it like, what's 1 plus 3? 4. What's 3 plus 1? 4. So they wind up kind of at the same thing, but they're just kind of oriented a little different. Does that make sense to folks? Great.
Symmetric matrix. I looked this up today to make sure I had the right word.
Yeah, my matrix algebra terminology is very rusty. So Ahmed, you asked about 4 fixed effects, 4 variances, and covariance. And right now we're only dealing with variance and covariance. So we don't have any predictors yet in the model. So once we get to predictor land, then those parameters start counting as like number of parameters in the model. Lisa, go ahead.
I was going to say, I did not reference what kind of model for the means I was talking about in questions 1 or 2, because I'm just focusing on the variance part. So you're correct in that generally we would count the number of fixed effects, but I was deliberately ambiguous as to what they would be here so that we would focus on just the variance side. So variances and covariances is the thing we would keep track of with respect to that.
Okay, thank you so much.
Yeah. Are there other questions for folks about this so far? Okay, bonus question. How many, oh, just kidding. I'm not going to ask you that question. How do we estimate, how do we know how many parameters we have in terms of our variance components for unstructured? How did we arrive at 10? Is another way to ask that question. Yeah. Well, very close, Ahmed. I think it's supposed to be a plus instead of a minus. Yeah. But you were spot on and you were quick. So there's actually a formula that we use, and it's n times n plus 1 divided by 2, where n represents the number of occasions. So that's why we wound up at 10 for 4 occasions. And this can just be a yes or no. Is the number of parameters going to change if we change the number of occasions? Yeah. And generally it goes up, and it goes up very quickly. Great. Okay, so then I just have one final, like, we kind of drilled in to look at specific variance modeling choices. And now I kind of just want to zoom out a little bit and talk about these things kind of together. So between compound symmetry and unstructured, which is going to use the fewest parameters, which is also known as most parsimonious? Yeah. Lots of CS's. Compound symmetry. Yep, we are only using 2. It doesn't matter how many occasions we have. Between compound symmetry and unstructured, which one is going to fit the best? Fit. Yeah. Great. And so I just wanted to highlight this slide in terms of like where we are big picture. I kind of talk about these, a few of you have come to office hours, and I've talked about these as kind of like the goalposts. Like we're trying to figure out, you know, best fit while also not using 1.5 million parameters to estimate these things. And my final question for you all is, are these the only 2 options for variance and covariance patterns? Yeah, great. Correct is terms, no, there are not other options. No, I said that backwards. Yes, there are other options. Oh, great. And I'm going to hand it off to Bladimir, and we're going to talk a little bit about those later on.
Yes, 2 things if I can interject quickly. Ahmed, your version of the formula would give you the number of covariances. So that version is actually useful for figuring out that much, but eliminating the variances. And 10, your answer would be correct if you said how many patterns are possible in ANOVA land. There are indeed only 2. And that's kind of the point I was trying to make here also, is that least squares gives you only a limited set of options. Switching to some kind of likelihood expands the menu of choices that you have.
Great, thank you.
Hi, so that's my turn. Thank you, Lisa. Thank you, then. So, yes, I will be covering questions 3 and 4. I read your answers. Thank you so much for your time and thoughts about those 2 questions. Now, regarding question 3 specifically, question was, how does the content of the variances and covariances over time in the R matrix differ when a G matrix is used or not? The G matrix containing at least a random intercept variance. Someone can help me with this one? How does the content of the R matrix change after including a G matrix or when we don't have a G matrix in our model? And I'm reading the chat windows too, so you can talk or write down. Yes, some answers. G matrix introduces the level 2 variance. Yep, but that's not how the R matrix changes, right? R-only metrics, both level 1 and level 2 are included, while the G matrix contains only level 2 variances. Yes. So what's the R matrix after including the G matrix? That's what I'm looking for. In a model without a G matrix, the R matrix contains only the residual variances of the observations. In contrast, when a G matrix is used, the residual variance in the R matrix may be smaller since some variability is attributed to the random intercepts. Yes. Yep. We have a combination of all of your answers, so thank you for that. Now, more specifically, we know that, yes, thank you, Lisa. Residual, after including G, residual in the R matrix means the leftover part. Residual meaning level 1, not just leftover. Yes. Yeah, but well, you can explain that later, Lisa, because to me, after we include the G matrix, well, I should explain the other thing first. When we have R only variances, well, variance covariance matrices, the R matrix is trying to recreate the total parent of variance and covariance in our outcomes, right? R only metrics. However, we know that in longitudinal analysis, when we have repeated measures, there is some kind of dependency in our outcomes. So we know that part of the variance in our results are because of people, and we know that we can have people mean differences. So I think that the key one of the key ideas here is that we are removing or we are splitting that original R matrix into something between people and something within people. So in that case, the R matrix becomes something different, like just the within people residuals. And we are allocating part of the original variance into the G matrix, which contains the random intercept variance, because we know that part of the variability comes from the between people mean differences. Now, can you explain, Lisa, what you said, residual, meaning level 1, not just leftover?
Yeah, the word residual is highly contextual in terms of what it means. So, like when you see residual variance as a parameter on your output, it means leftover. So, if you have an R only model, then all the leftover variance is in one matrix. And so that's why they call it residual in the leftover sense. When you add G, the definition of residual switches to not just be leftover, but leftover at level 1 specifically. That's what I was trying to say.
Yes, and I agree. But do you have more questions about these two concepts? Because reading your answers, I think that most of you were able to identify these distinctions. However, do you have any other thoughts or impressions about this difference? When we don't have the G matrix in our model, the R matrix tries to what was the word? Recompose maybe? Yeah, the total variance and covariance of the residuals. However, after we accounted for person mean differences at level 2, introducing a random intercept in the G matrix, specifically the random intercept variance, not just the random intercept. Now the R matrix is what remains after accounting for that variability. So it is specifically the within person residuals. Is that clear? Do you want to hear the same thing with other words? You can say anything, come on. I can try. Clear? Great, okay, yes. If there is something else that you would like to discuss, you can attend office hours or ask after classes too. So don't feel shy. Now,
I have a question, if I can.
Yes, go on, please.
So I'm thinking about clustered models, just more broadly. And I'm wondering why we're using matrices more here. Like, why are we introducing G and R and V and all of that, like, at this point? Because matrices are, I don't understand them mostly. But I understand, like, some of the other things in the cluster model class. So, like, I'm just curious why, like, now specifically.
I would love this to be a decision, but this is not a decision, I think. This is what the model is doing. Well, it is a decision if we introduce a random intercept in our model. That's a decision. So the idea to me is that we are just trying to understand how the variance partitioning is working. In longitudinal data and in cluster data, we know that part of the total variability in our results are because of mean differences between people in the first case, between clusters in the second case. So if we know that the primary source of variance across outcomes, for example, is related to person mean differences, I think that for us it's pretty reasonable try to take that component of the variance, that pile of variance, and try to move it to another matrix. In this case, I'm talking about the G or T matrix. In some texts, they talk about the T matrix instead of the G matrix, but the content of that matrix is the same. We are reallocating part of the total variance to the G matrix because we know that the primary source of variability in our outcomes are related to cluster or person mean differences. So That's pretty important because when we say that we are introducing a random intercept in our model, that's what we are doing. We are reallocating variance from the total, from the pile of total variance towards the G metrics, because we are assuming that the primary source of variability is due to person mean differences or cluster mean differences. Do you want to add something, Lisa?
Yeah, I was expecting this question actually, and I think I can answer it in a way that is a little more direct. In cluster data analysis, there are no other kinds of matrices for R besides diagonal. That's why. So diagonal meaning just variances on the diagonal, zeros on the off diagonal, because people in clusters are arbitrarily assigned to, like, this is person 1 versus person 2, and you could switch them around and it doesn't matter. They're truly exchangeable. So a random intercept induces that exchangeable covariance structure. In contrast, occasion 1 and occasion 2 are different things. You cannot switch them around. And so in longitudinal data, there's these autocorrelation patterns. Residuals from occasions closer together in time are usually more related than residuals that are further apart. So there's this extra set of choices we have to make because of time as a design factor that just doesn't exist in clustered data land. Does that help? Okay, and I don't like matrices either, for the record. So that's why I call them piles. Or you can think of them as like little houses in a neighborhood. Like your parents are going to go live in the G matrix and the kids are going to go live in the R matrix. And it's a lot easier to get along that way if not everybody's under the same roof. I get along with my parents much better now that I don't live there. I'll tell you that much. Hi, Mom and Dad. You. Does that help? Okay.
Yeah, and I would like to add that to me they are important because based on the decisions we make is how can we interpret our results later. So that's why it's important what kind of R metrics we have, or if we add or not a G metrics, for example. So any additional questions? Thank you for your question, Hilary. Thank you. Anyone else? 1 to the 2 to the 3. Okay, let's move to question 4 because this was hard. This was hard when I took the course 2 years ago, and I'm pretty sure that's still being hard, this question, because now question says, how do the distinctions of balanced versus unbalanced time and equal versus non-equal time intervals between occasions affect which ACS, alternative variance structure, models are possible to consider? So, based on your answers and after considering some things about this specific question, Lisa prepared a specific spreadsheet that she can share, so we can try to discuss some things related to these concepts that can help you to understand some differences and common points. Go on, Lisa.
No, I just shared the wrong thing. I'm trying to share the whole screen and not just the app, but here we go. Yes. All right. So I will post the completed version of this after class. You do not need to type. I just wanted to try and organize our thoughts. And I came up with this morning, and then Vladimir reminded me that I did the exact same thing 2 years ago. And so I looked at the old spreadsheet and my new one and tried to put them together. So this is an evolving way of trying to conceptualize these things. But I think in terms of spreadsheets. So this is just like how I approach the world. So I will do the recording as Vladimir sort of leads us through the sets of choices here. Can you all see the font? Is it big enough? It's okay? All right. Then take it away.
Yes. So I will try my best, and I will need your help here. Because as you can see in column A, we have all of the R matrix choices that we have seen in class. And through columns B and F, we have different options or criteria that we can use to make a decision. So first, we have CS that stands for compound symmetry. So we know that when we are using a compound symmetry structure, in the R matrix, we have just one number in the diagonal of the R matrix, which is, what do we have there? In the diagonal of the R matrix when we are using, yes, Hilary, variance. And we have only one variance. That's the same number across all of the cells that we have in the diagonal of our R matrix. Now, in terms of the covariance structure or the pattern of relationship that we have for our covariances or correlation, do we have something like a lag involved in the compound symmetry? No, right. So we don't have that. Now, in terms of the number of parameters we are estimating, we know that the variance is constant. Also, the pattern of relationship is constant. So regardless of how many occasions we have in our data, we will have one variance and one covariance. Now, this is relevant for the other two characteristics of this R metrics. Do these metrics require balance time? The answer is no. Why? Because we are estimating only one variance over time, only one. So that variance will be the same regardless of the time point we are analyzing or regardless of the occasion we are looking at. So it doesn't matter if you have time as a discrete variable, let's say at time 1, time 2, time 3, the variance would be the same if you have something like occasion 1.1, 1.2, or 1.7, depending on the metric you are using for time, because at the end of the day, we only have one variance in the diagonal. Now, does this structure require equal time intervals? The answer is no. Now, why? Because again, we only have one parameter to describe the pattern of relationship among our covariances or correlations in the R matrix. Questions about this first example? Because now, using this as a reference, the ideas and things that we mentioned, we can answer, or we can fill the cells for the other matrices. Questions? Okay, so let's move to the compound symmetry heterogeneous case. Now, what kind of variance do we have in the diagonal? In the heterogeneous case. Of course, yes, heterogeneous, yes. I said, sorry. Yeah, so now we have a compound symmetry heterogeneous structure. Do we have something like lags here? Is the idea of lag involved? What do you think? No, exactly. No, isn't it? Why? Because in both cases, in the compound symmetry homogeneous and compound symmetry heterogeneous, we have one number to describe the pattern of relationship across residuals. Okay? So we are not changing that. What we are changing is the diagonal, the variances. So how many variances do we have now? I have one for n, other for 1. Someone else, how many variances do we have? Heterogeneous case. Let's say that we have, yes, n. So that's because now for each occasion, for each specific occasion, we are estimating one specific residual variance. Exactly, as many as occasions we have. That's why Lisa typed there n variances, because that will depend on the number of occasions, and occasions is equal to the number to n here. Now, yes. Question, Hilary?
Yeah.
Yep.
So it's only one correlation, even though like if we were to look at the actual numbers in the cells, they would be different, but it's one correlation because that's all we're estimating, because it ends up being that correlation plus the variance. Is that why it's only one correlation?
It is one correlation because we have different variances now. So the covariances will be different, I think. So we need the correlation there. Right, Lisa?
Yes, it is one correlation. So if you looked in the correlation version of the matrix, it would be one number. When you back translate that to covariance, it would be different numbers because the corresponding variances are different. So that's shown on this slide here. The CSH is one number that then multiplies the standard deviations of their respective occasions to become the predicted covariance. So that's why I use the term ingredients, because like these are the parameters that are being estimated that together build the pattern.
Yep. So now, in terms of balance time, this is interesting because in terms of balance time, what do you think? Do we need it here? What do you think? Yes, exactly. Now, based on the fact that we have different variances for this specific occasion, we need balance time. Otherwise, would be so hard for the model to estimate all of those things, I think, if we have unbalanced time, because now we can have something like, instead of just 1, 2, 3, we can have 1.3, 1.7, 1.8. So the R metrics, I think that the model would have problems to estimate all of those things at the same time. So yes, we require balance time in the case of the heterogeneous variances. But what about equal time intervals? What do you think? Have we changed this idea of equal pattern of relationship across outcomes? I don't think so, right? Because we're still having only one number to describe that relationship. So regardless of at what specific time point you are looking at, the relationship is the same. So we don't need equal time intervals for this specific R metrics. Questions? Exactly. Yes. Yes, Hilary, because we have only one number to describe all of those relationships. How do you feel? Yes. So is that like could be better? Yes, I think that's like could be better, but we are not bad. So you can take that.
Can I
Yes,
ask a question?
of
Can
course.
we say then that the answer to columns E and F correlates with the answer to columns B and C? Like you require balanced time if you are looking at a heterogeneous structure, and you require equal time intervals if there's a lag?
That's why those things are there. Yes, they
Oh,
exactly. Yes.
thank you. This is helpful.
So all of these criteria work together for us understanding all of these things. Okay. So yeah, thank you, Rebecca. Now let's go to the unstructured option. Yes, thank you for your comments. So in the case of the unstructured R metrics, what kind of variances do we have? What do we have in the diagonal here? Exactly, heterogeneous variances. Why? Because in the unstructured R metrics, we are estimating as many residual variances as occasions we have. Now, what about the relationship between those residual variances or the occasions? Do we have something like a lag here? No, exactly, Ahmed. We don't have lags yet. Not necessarily, yeah. I would say that not. We couldn't have lags here because we are not forcing different occasions to have the same pattern or the same relationship. Exactly, yes. Lags are constant relationships. For example, then we would talk about that in the case of the autoregressive ones structure. You will see that we are estimating one correlation between occasion 1 and 2, which is forced to be the same as correlation between occasion 2 and 3 and 3 and 4. Yes, because that's the idea of a lag. But right now we are just estimating or describing the whole pattern of variances and residual covariances in our R metrics. So how many parameters can we have here? Yes. Infinity, oh, fortunately not yet. But yeah, as Lisa said there, we will have all of them. We will have as many variances as occasions we have. The number of covariances, we know that it is n plus n minus 1 over 2. Yes, all of them, because that's what the AND structure means. So, given these conditions, do we require balance time for this data? Exactly. Yes. Yes, we need it because we are estimating different variances. So each occasion will have its own residual variance. We need balance time. But what about equal time intervals? Exactly, we don't need it because we are we are just estimating those relationships in our R metrics. So we don't require equal time intervals. Thank you, Lisa, for highlighting that because that's the relationship or that's the pattern that we are discussing here. What's the relationship between the type of variances and residual covariances that we have and the idea of balance time and equal time interval? Questions? How's this going? Better than 20 minutes ago? For sure, right? Thank you for your reactions. So now, this is tricky, standard autoregressive. Do you want to explain this, Lisa? So I can explain toplets and toplets heterogeneous. Okay?
You want me to do these 2 rows?
Yes, please.
Or these
Yes.
3 rows? Yes.
Well,
I was
those
also
three.
just off topic comment. I feel like a smarter version of Vanna White happening right now. Like on Wheel of Fortune, she's the one who turns the letters around and while things happen. So I'm like narrating with my gestures what he's saying. So it's kind of fun. This is like a different sort of, teaching dynamic here. Yeah, so I'm making a distinction as to what is sort of baked into standard software as a pattern that you can ask for, which is AR1 and a heterogeneous version, versus a different option that takes into its specification a variable for continuous time. So in a standard AR1, time is discrete. In the continuous time version, it can be truly a quantitative variable, just like as would be required by unbalanced time, essentially. So that sort of gives away the answers. But in standard autoregressive, is this one homogeneous or heterogeneous? And there's no H on it, so there's your clue. Yeah, homogeneous. Are we based on some kind of lagged pattern? Yeah, this one is. This is where occasions 1 unit in time apart are correlated R, 2 units in time apart are correlated R squared, 3 apart is R cubed, and so forth. So that is the idea that 1 and 2 are just as correlated as 2 and 3 are just as correlated as 3 and 4, and we call that lag 1. So the first off diagonal would have the same predicted correlation. So then that means, in terms of ingredients, only 1 variance and 1 correlation. So this is another instance in which it would be 2 parameters no matter how many occasions you have. Does it require balanced time then? It does if time is discrete. That's basically another way of saying it. And it does require equal intervals, I would say as well, because of the lagged specification of the correlation structure. Changing to the heterogeneous version, I would say yes, it's heterogeneous. It's still based on a lagged pattern. How many variances would I have in here? One variance, or n variances, excuse me, and then the one correlation. Yep. So this is following, by the way, in lecture 4. I'm going through this list here. It's the same idea in terms of the heterogeneous version. There is a common correlation that is then multiplied by the corresponding standard deviations of the occasion variances to become the predicted covariance. So the covariance does not follow the pattern, the correlation does. Okay. Does it require balanced time then? Note the correspondence between columns B and E. Yes, it does. And does it require equal intervals? Yes, it does. So this one then, this is a little bit tricky. I have never seen a heterogeneous version of this one. I don't think it's possible for the same reason that we wouldn't have a heterogeneous version of any unbalanced time. You'd have to have as many separate variances as you have unique time occasions. That is not going to work. So this is a homogeneous structure. It is still built on a lag. The only thing is that it extrapolates what the correlation would be for things that are further apart. So it's the same idea, but it acknowledges the fact that you have these unequal intervals that you're working with, but it tries to structure the correlation pattern as if you would have, what it would have been essentially to make that work. So this is another one that has one var and one correlation. I would say no-ish under these ones, and the same thing here. So it's operating as if it's AR1, but it is trying to sort of fill in the gaps as to what continuous time, how those things would need to be adjusted. So I'm going to say yes-ish. Actually, no. I'm going to say no. I'm going to stick with my first answer. Does not require balance time. So this one is very helpful in practice, I would say. This is what, so those of you who are familiar with the dynamic structural equation modeling type of thing, have you heard this term before? This is the mutanes trying to like relabel stuff to sell their software. Dynamic structural equation modeling adds in lagged effects for previous occasions. And the way that it does it is you have to basically tell it what your interval is. And then there's some mathematical process that they use to try to like kind of fill in the gaps so that it looks like it's equal interval even if you don't, and then it estimates the model that way. So it is still based on the same principles, but it's more flexible in practice. Yeah, Rebecca, this one is the tricky one. This one kind of violates the rules, but this is a non-standard structure in terms of like the ones that are sort of built into software and built into textbooks. I just want you to be aware that it is out there. It's a little bit harder to find in software. The other ones, though, I think you can make a generalization that B and E map onto each other. Any structure that has heterogeneous variance requires balanced time. Any structure whose correlation pattern depends on the idea of a lag requires equal intervals to pull that off. Those were the conclusions that I was hoping that we would reach. And y'all beat me to it.
So for standard AR1, it's homogeneous, but it requires balance time.
Yeah, there's no extrapolation that's part of the process, essentially.
Can you say that another way?
No. Can I think about it and try to get back to you?
Yes, I'll accept that.
Okay, yeah. This is one of those things where I read the description of the extrapolation and it makes sense, but that's all the content I came back with in terms of trying to recreate what I've read. Let me see if I can come up with a description of it that someone else wrote who knows what they're talking about. Would that be okay? All right, yeah. I'm try to be the first person to admit when I don't know the answer to something, and that is the best I can do right now, but I will try to get back to you. Okay, Vladimir, do you want to do the last two?
Yes, of course. Let's finish this. And yeah, I think that again, we will have something weird here. Yes, you will see what I'm talking about now in 1 minute. Because when we have doublets, Yes, and that's my pronunciation. I think that there is not a correct one. Toplets. Well, so what about variances in the standard version of toplets? What do we have there in the diagonal? Homogeneous or heterogeneous variances? Yes, homogeneous variances, because we just have one, right? Now, in terms of the relationships between those residual variances, do we have something like a lag here? Do we have lags, also known as bands? Yes, we have. And how many parameters do you think that we have here in the standard version of toplets? We know that we will have one variance because it's homogeneous, but in terms of covariances, how many lags or bands can we have here? Yes, Rebecca, yes, yes, n minus 1, exactly. N or n minus 1, the total would be n, right? Yeah, because if we have 1 plus n minus 1 is n at the end. So yes. Now, given that we have homogeneous variances, do you think that we need balance time? Homogeneous variance in the diagonal, do we need balance time? Yes, I would say no. However, Lisa, can you update this answer? Because 2 years ago, we knew that no software could do this. So we had to use a toplets structure with balance time. So maybe this is an interesting update.
Yeah, no, that might have just been a mistake because regular flavor toplets is a homogeneous variance model.
Yes, exactly. So my answer there would be no, because it is homogeneous. However, I remember that 2 years ago, we discussed the idea of software availability to do this. So that would be an interesting update, maybe. Now, do we require equal intervals in time? Do we need it? Yes, we need it because we have the idea of lag or bands involved. So finally, applying all the things that we have learned here, when we have a toplets heterogeneous, what kind of variance do we have? What's in the diagonal here? Heterogeneous variances, exactly. Do we have bands or lags involved? Of course we have, because that's toplets. Now, in terms of parameters, what's the main difference? In the variance part, right? Instead of just one variance, now we will have as many variances as occasions we have, but the bands or lags will be the same. We can have up to n minus 1 correlations because variances are different. Okay? Finally, in terms of balance time and equal intervals, do we need both constraints? What do you think? Yes, yes, and yes, exactly. Yes, thank you. Why? Because now, given that we have different variances in the diagonal, we need balance time. And given that we have the idea of lag or bands involved, we need the distance between occasions to be the same. Otherwise, it wouldn't make sense to talk about these things. So that's all. Questions, comments, impressions? Do you think this was useful? I think so. So I hope that this helped you to have more ideas about the things that we were asking in formative assessment. If you have any additional thought, comment, or question, you can attend office hour or ask in class. So that's all. Thank you, Lisa, for the time, and thank you for your answers.
Yes, thank you to both of you. Excellent review. Just one more point I wanted to make while I had this up. So the same thing happens with the heterogeneous models in compound symmetry and in topolits. The covariance that's held in common in the homogeneous version switches to a correlation that's held in common. That correlation then multiplies the corresponding standard deviations of those variables to become the covariance. So then it's the lagged pattern follows the correlation, not the covariance, as long as you have heterogeneous variances. Couple questions. Glad you like the spreadsheet. Yes. I will put it back up so you can take a screenshot, but I will give you the right answer after we're done. So here you go. Question, why CS and CSH do not require equal interval? They're not lagged, but they're like a more strict version of topolits. Yes, I can answer that question. 1 second. Go back to this pattern. So I would say that because the correlation is constant over time, it doesn't care how far apart the times are. There's no changing the correlation based on the distance in time. It's all one number. So that correlation pattern doesn't care whether the occasions are equidistant or not, because it's just one value regardless. Does that help? Maybe. Yeah, big picture, if you have heterogeneous variances, you can only have so many of them. So that requires balance time. Otherwise, you'd have a separate variance estimate for every possible occasion, and things are going to start to break down. And if anything is based on a lag, as in terms of describing the pattern of a relationship, equidistant occasions would be the only thing that makes sense. So those are sort of the take-home messages of the whole process here. Other questions? Vladimir, go for it.
Yes, Lisa, I have a question related to something that I've been thinking about, and I cannot solve it by myself. So we know that when we have unbalanced time and non-equal intervals, the option of combining G plus R matrices is a more flexible way to model what we have, right? However, we also know that once we added the G matrix, we can have an unstructured R matrix. However, we can also pick other options for the R matrix. So we could combine a G matrix, let's say with an autoregressive one, R matrix. So in that specific case, this idea of lags comes to the discussion again. So to me, if lags are involved, balance and equal balance time at least would be required. So to me, it's kind of confusing thinking about this. Could you say something about that?
Yeah, I think it has to do with the implementation. So like if we just pretend this cell doesn't exist here, then it follows the pattern. Anything that's homogeneous does not require balance time. Anything that has some sort of a lag does require an equal interval. And that does not change, by the way, if we're using a G matrix or not. So the R matrix by itself describes all of the leftover variation and covariation over time using these patterns. If you add a G matrix, that means you're partitioning the total variability into between. Those random effect variances and covariances will go live in the G house. Can I say G house instead of G matrix? Does that make it better? Okay, so they go live in the G house. And the remaining level 1 within person E residual variances and covariances go and live in the R house. So these R house structures work no matter what they're operating on. It's just the conclusion would be different. Cough, cough, homework question. So for instance, if you have a random intercept in an AR1 model versus just AR1, those say different things about what the AR1 correlation is applying to. So if it's an R only AR1, then the entire pattern is autoregressive, the total. If it is just the within person part that has the autoregressive correlation, then the E's are what have that pattern, not the total. So the rules are the same, it's just what is the content they're operating on. Is there still a contribution of between person mean differences, potentially, that's being put into this pattern, or have we separated that out so that the pattern that remains can likely be more parsimoniously estimated? Okay, did I answer your question, Vladimir?
Yes, but
Okay.
I have a follow-up question because yeah, your explanation was clear. So to me, what is confusing there is that even when our R matrix contains the leftover things or the within person residuals, once we have that R matrix, can we use lags? And
Hmm?
if we can do lags,
Yeah, you can.
why now? After including the G matrix, why now we can use lags with non-equal time intervals? To me, that's the hard part.
Oh, okay. Then I misunderstood your question. No, in standard AR1 implementations, where there's no extrapolation and time is treated as discrete, then it does require equal intervals because then you're still working on the idea of a lag. But it's what does the lag apply to? It is structuring the E correlation pattern, not the total correlation pattern, if you have a random intercept in the model as well.
Yes, that was my question, Lisa. Great. Because to me, it was pretty weird to say that when we have unbalanced time or non-equal time intervals, we can use the combination of G plus R when we know that some R matrices require this balance or equal time intervals things. So to me, it was like, okay, so what's doing G that after including it, we can use those R matrices that require balance time or equal time intervals. But based on your explanation, so we have some constraints, right?
Yeah. Yeah, the
Awesome.
continuous
Thank
time
you.
version is what makes it different, but that's a different implementation of the same idea. And it's less common, I would
Very
say.
clear.
It's a
Thank you,
relatively
Lisa.
newer thing that's possible, I would say, more generally.
Thank
And
you.
then added to these ones that we didn't talk about, there was a question in class about AR adding a random shock. That's MA as a pattern. I didn't present that in class, but you can have MA moving average is one of them, and then you can combine the two called ARMA. And I believe you need at least 4 occasions or something for those to be separable. I don't remember off the top of my head, but I know, but there's other kinds, point being, that are built into standard software that you'll come across. Okay, any other questions on this? Because we can try to work on the G and R versions of the models. Finish that up. Okay. Then let me pick back up. Let me see here. I'm going to kind of switch back and forth, I think. We'll do them sort of one by one. So the idea of, here we go, reviewing terminology here. The idea of G and R is we know that the most prominent source of correlation of occasions from the same person is going to be person mean differences. That is a universal phenomenon in almost every research study I've seen. And so it makes sense from an economy perspective to take that source of correlation and partition it out of the way. So we put that source of correlation as implemented via a random intercept variance in the G matrix, which is level 2 between. And I want to be very careful about my terminology. When I say random intercept, I'm talking about like the U in the equation. Okay, I would call that a random intercept. Random intercept variance is the variance of the U's. Like that is what goes into the G matrix right there. So more generally, the G house matrix is going to hold our level 2 between person variances and covariances via random effects. For now, just a random intercept variance, eventually adding random slope variances of different kinds. And then what's left in R is within person level 1 E specific variances and covariances. So in the same way, E is this is a residual right here. Sigma squared E is the variance of the residuals that shows up in the matrix. So it's the collection of them that we're focusing on. So when we do it this way, we can still put them back together again to get a total predicted pattern, and that pattern is called V. So G and R put back together again gets us to the same place that the R-only model started from. It's just potentially a more efficient way to structure. So from that perspective, we looked at a couple baselines. So this is how you can put together in your head some important equivalencies. So the simplest possible model, our compound symmetry model, you can set it up in 2 different ways. The way we started with is this way down here. That's an R-only model where we have something called a CS parameter and a residual variance. They work together. The sum of those is the total variance over time. And the CS part is what the source of the covariance would be. That is the exact same thing as V over here with different notation. So V ends up at the same place. It just accomplishes it in a different, more indirect way. So random intercept variance plus this is a diagonal R matrix right here works out to be still the same compound symmetry pattern. So people might call this a different name. Like people would call this one down here compound symmetry. People would call this one random intercept only. That's a semantic distinction, but they're referring to different ways of getting to that place. Likewise, we can conceptualize an unstructured model as something random intercept plus something in R, and this is the most complex R pattern you could possibly have with once you have a random intercept variance in G. So V then is composed of between person mean differences variance, level 2 over here, pre and post multiplied by a column of 1 so that it's the right size to add to R. And then R here has heterogeneous variances of the E's on the diagonal, and it has whatever correlation pattern you want among the E's, or covariance pattern, excuse me, on the off diagonals. So this is still, everything gets to be what it wants. But you can't spend all possible parameters. You can't estimate everything separately and still have room for a random intercept variance left over. So to make sure that we don't go overboard, get overdrawn from our account, so to speak, we shut off the last lagged relationship. So the first occasion and the last occasion in the R matrix are set to be uncorrelated. What we are saying is that they're not uncorrelated. They're uncorrelated after controlling for person mean differences via the random intercept variance. So random intercept variance is the only reason that occasion 1 and occasion n are correlated. So this pattern then allows us to potentially see, okay, this is as much as R can have. The alternative is that one. Something in the middle might be necessary. So no correlation of the residuals after controlling for random intercept versus all the possible correlations. So there's choices in between that we can use AR1 and Topolitz for. And this one in particular is harder to find in software. There was a question in class last time that I want to reiterate here. If you can't estimate this, that's okay. All you really need in terms of doing model comparisons is the log likelihood from an unstructured model, because it is likelihood equivalent. It is a rearrangement of the same thing. So random intercept plus UN n minus 1 here is the same thing as an R-only unstructured model. Okay, does that make sense?
To clarify, when you say log likelihood, you mean -2 log likelihood or different thing?
Either way, it depends on what your software is, what you get by default. But log
Okay.
likelihood is the primary ingredient. Once you multiply that by -2, then it becomes -2 log likelihood. So both
Okay.
of them should be equivalent
Okay.
to what you would
All right.
get. Yep. Thanks for the question. I can give you an analogy. Would that help? Maybe. I can try. So I used to watch the show Hoarders on A&E and other channels, which, if you're not familiar, are folks who have a habit of collecting things, even when those things are not valuable or useful. Sometimes it's they're shopaholics. Sometimes it's disability-related reasons. They have low mobility and they can't, take their trash out and that kind of thing. And trying to clean up a hoarded house and try to figure out what to save and what to throw away is very challenging, especially because it's just all jumbled together. So the first thing that they have people do is they start clearing things out and they start sorting them into piles so they can see, like, how many forks do you have? How many pink sweatshirts do you possibly need? And trying to organize these things makes it easier to sort of pare it down and work with what's left. So I think of like the original unstructured model, let me get back to that here, as, where is it? On the first slide, there we go. Like the original version is like everything's still all jumbled together, and it's less you're less able to see what is there and what are the ingredients that are causing the jumble, versus the version what has the random intercept taken out is kind of like the sorted version. Like you're trying to like let's throw all the trash away first, and then we'll look and sort what's left. Does that help at all?
So
I'm trying.
using the G matrix is like sorting all the stuff.
Yeah, like if the primary source of the clutter inside the home is garbage, right? Like and that is honestly what happens a lot of the time in the show. Like it's literally just garbage that never got taken out. Soda cans, pizza boxes, piles of trash. Like if you can clear out the garbage, go put that in the G house. Not that person main differences is garbage, but we're working the analogy here. If you can clear out the garbage and put it somewhere else, then you can more clearly see what is left and how you might deal with it in terms of giving it away or keeping it.
Which, when we're doing longitudinal stuff, like we care about the time. Like we're really focused on the time. Otherwise, we would just use like a standard model without time. Like,
Yeah.
okay.
Yeah, people who go to the trouble to collect longitudinal data usually care about time. Like, I mean, why else would you go to that trouble? So getting the time correlation pattern right before you start tackling all the other things you care about is really important, because otherwise the test of the fixed effects downstream are probably going to be some shade of wrong if your model for the variance and covariance pattern over time isn't supported by the data. Other question, can we go the other way, estimating an R-only matrix and try to decompose it into level 1 and level 2? Yeah, I mean, I sort of see that as a semantic distinction. It's like you telling your software the way you want it to set up. It's like, okay, I want a G matrix that has a random intercept, and I want a diagonal R matrix. And it's like, okay, here's your result, it's compound symmetry. Versus you telling it, I want a compound symmetry matrix from the first place. Okay, here's your result, it's compound symmetry. The advantage of having the random intercept then, like I said, the rest of the semester we're going to have G and R operating, because this is where we're going to add to it. This model says that the only source of person dependency in terms of creating correlation is mean differences. Well, the next logical thing would be like, well, what about slope differences? What about people changing differently over time? That will contribute to the G matrix as well, further partitioning variability out of the R matrix. So right now, what looks like it could be due to just whatever pattern could be a result of hidden random slopes that we don't have accounted for yet. Okay, did that help at all?
Yes, thank you.
Well, thank you for lying to me if it didn't. I'm trying. This stuff is hard. So I've taught, I think, 7 different courses at the graduate level in my career. And the feedback that I've gotten from folks is that this is the hardest one. No matter where I work, no matter who I'm teaching, like everyone says this one is the hardest because there's just so much terminology, so much notation, and a lot of it is very abstract. So you're in good company if you're like, this feels hard. It does get better with practice. So once you get a hang on the terminology and you can just whip off the top of your head, oh, level 2 is between, is G, is random, is persons, is like, once all that sticks together, and that I'll keep doing that, we can do it. Level 2, between persons, individual differences, live in the G matrix of random effect variances and covariances. Person things are going to explain that. Level 1, within person over time. That variance and covariance lives in the R matrix of the residuals, and the only thing that can explain it is time varying things. Right? Like I have a PhD every day. That, as a predictor, cannot explain why today's class feels harder than Tuesday's class, or vice versa, right? That's a person constant thing. Maybe the fact that I'm distracted by my child being sick made today harder than Tuesday. That's a time varying thing. We all have those things that create fluctuations relative to our own personal baseline. That's the source of variance and covariance that the R matrix is supposed to cover. We also have things that we bring with us all the time that are person characteristics, and those are the things that are going to explain the variances and covariances in the G matrix at level 2. Okay, 143. Looks like not only are we not starting lecture 5 today, we're going to revisit this next week, but that's just fine. It takes as long as it takes. All right. It's my pleasure. Honestly, this is why I have this job. I thought I was going to be a stats consultant, so I went to do a postdoc to learn more about models. And then I got a chance to teach, and it was really transformative, and I thought, this is what I need to do. So I thought, you know what, I'm going to fake a research program long enough to get tenure so I can keep doing this. And that worked. So this is what I like to do. So thank you. I really appreciate the effort that you are all putting into trying to learn this stuff, because it is not easy. But if it were, then you'd be wasting your time and your tuition dollars, right? That's the way I look at it. Okay, 144. We will call it a week. Thanks for being here. Let me know if you need anything. You can be working on homework 1. It is due Wednesday. Me and the TAs are happy to help answer questions, okay? All right. Bye for now. Thank you.